without further ado, how to robot in IEEE tale. So I want to start with a few robots that exist in the world to give you an idea of the climate of robotics. So Wistful Big Dog, here he is remembering a breakup, walking along the beach. They're getting close to sentience. They can remember breakups. The Big Dog is built by Boston Dynamics, who were recently acquired by Google, in case you thought they weren't trying to take over the world. It's a four-legged robot that can balance itself. It's an incredible machine. You should look at videos on YouTube. Kristen Stewart.
She's only sort of robot.
And my favorite, Falcon 9. So most people don't think of rockets as robots, but they are. And if you ask Andrew Howard, the GNC lead at SpaceX, he'll tell you Falcon 9 is a robot. It's a machine that thinks autonomously. It figures out how to do the things it needs to do to get into space without anybody driving a joystick, or as we like to say, any interns packed in the cockpit spinning it around. There is a computer inside that says, okay, I need to reach these altitudes in this sequence, gimbal the thrusters in this way, and it's not pre-programmed. I mean, the concept is programmed, but it uses sensors to figure out how to respond to emergencies. So if wind starts blowing and they don't expect it, the thing knows how to respond. So our robot, I'm going to jerk myself off for a little bit. We built this nice ass robot. It has a badass arm. So we based the arm off of the ABB IRB 420. 420. Why is that in a robot arm name? So it's a parallel linkage mechanism. If you look in the front, actually I don't think most of you can see that. I'll show you after.
Can you put it up here?
Don't do that.
This is our robot. There's two servos in the base that rotate the arm. Now, unfortunately, the servos are fried, so I can't show them working, but I'll show you a video. So there's a parallel linkage that forces the end effector of the arm, which is the wrist of the arm, to always be parallel to the ground. Really clever design. Our mechanical lead, Jason, came up with it. So if you forgive me for one more masturbation reference, I think a great application of this would be coming next. Let's go, no, please. So we have a full 3D simulation, because building a robot takes a long time, but we want to make the robot work before it's built. Most of the time, in fact, probably before the 70s, we want to make the robot work before we build it was a stupid idea. It doesn't make any sense. But now, we have this tool called Gazebo, which is a full three-dimensional simulation of the robot. So we basically imported the SolidWorks model, developed all of the physics, all of the dynamics, all of the constraint mechanics, and now we simulate the whole robot. So you can do everything that this robot can do on your computer, as long as you're running Linux. Funny story, so one of my friends, if you've heard of the DARPA Robotics Convention, they do like walking robots, very cool thing. He used Gazebo to simulate his robot, and he was in an interview at SpaceX, and he was talking to this guy, Andrew Howard, who I mentioned before, and he talked about how he used Gazebo, and he was saying that there were some issues with Gazebo. And he said something to the effect of, whoever came up with Gazebo should have been a better architect. And so there's a pause in the conversation, and Andrew says, are you aware that I created Gazebo? And I think it's one of the funniest things that could possibly happen to you in an interview. You got the job, but that's a pretty classic thing. Here the robot is performing a mating dance. This is how we get more robots. This is my favorite picture, realization. Most of the time I show this live when they don't see the actual robot. We designed a robot, and then there it is, there's the robot. The colors are different, but I mean, it's built. Here's a video of the arm in motion. Come on. So we're using ROS, Robot Operating System, on top of Ubuntu 14.04. So see this cute little super awesome GUI right there in the background for controlling the arm? So I made that in Pygame, and it took like 10 minutes. And on the right side is ls/dev. It doesn't have anything to do with the robot arm, but it looks cool. So here it is. You click a position. In the actual competition, the robot is determining which position the arm needs to go to. But there is something called an inverse kinematic solver, which figures out the optimal angles to put the servos at, to position the end effector at one location. Now, this is a really easy optimization problem because it turns out there's only two solutions for the angles of the servos, and one of them puts the arm broken. So we have one solution, analytical solution, easy peasy. none of that made sense, I would Google inverse kinematics. Oh, how the hell is this? Here we go. So how does it know what to do? I'm sure most of you are CS people, so you have some idea, but I want to give you a more firm concept of how it actually knows what to do. So step one is computer vision. I didn't mention this before, but the robot can play chess. It can't play chess right now because the servo's not working, but so it uses computer vision to segment a chessboard and identify pieces. And then there's an artificial intelligence inbuilt on the robot by a man named Josh Sanders, in case you know him. He's a senior, very smart guy. So it takes place in a sequence of steps. It takes a picture of the board, figures out which pieces are where, then passes that information to the AI on the robot. And that AI makes a decision about which piece to move. That decision is used to control the arm, which grabs a piece, moves it to a different position, and then the cycle repeats. And I want to be clear that there's really not anything else involved there. Well, so there's a lot of low-level sequences. There's power being moved around. There are all kinds of things happening in the operating system. But the way that we develop robotics is through a method called abstraction, so that people at each layer don't need to understand how things beneath them work. For example, the person developing navigation software doesn't need to understand how the hardware-level drivers on the motors work. And likewise, the person developing the hardware-level drivers on the motors doesn't need to understand how navigation works. That way, nobody needs to understand the whole robot. Now, it's obviously good if you do, but it's critical that when you have a 30-person team developing a robot that has 150,000 lines of code driving each part of it, you can't understand every single thing. There's no human being that could. Anyway, so another important component in our network is a Kalman filter. So Dr. Schwartz always likes to talk about Kalman filters. It's actually fairly simple. But the principal concept behind a Kalman filter is a filter of sensor data. So if you know where you are at one point, and you know roughly how fast you're moving, you can predict your future position. And there's a lot involved in the math, but our dear friend Rudolf Kalman, who used to teach at UF, by the way, came up with this really clever way of creating this sort of Gaussian distribution, something that ends up in this beautiful prediction of where the robot's going to be. So if you have faulty sensors, you end up with a prediction of where the robot is going to be that's more accurate than any of your sensors alone. For those of you who've taken statistics, you know that if you multiply two Gaussian distributions, you always get more certainty. So if you have 10 sensors, and all of them are fairly inaccurate, if you combine their input using a Kalman filter, you get more accuracy than any individual sensor. In fact, any combination of two sensors. I didn't take this picture, I got this off the MATLAB documentation, but the robot works similarly. We also use the robot operating system, which is a tool for passing messages around between different programs. For those of you who take an operating system, you probably already understand how this works, but we don't. So we use the robot operating system, which is a very advanced tool for handling message passing, computer vision, a lot of other tools. It doesn't do it for you, but it gives you the tools to do it yourself. This is a more complicated graph. This is from the subjugator. Okay. So, microcontroller. If any of you are in Micro P, we use the same microcontroller that you do. We just did a different word made by the same guy. What's there to learn? So this is a list of things that you can learn. It's a big text thing. But you're probably thinking, how could I ever possibly learn every single thing on this list? Now, one, you don't have to, but it'd be great if you did. But two, so there's a sophomore on our team named Christine, who started roboting like 2 months ago and developed a utility called SLAM, Simultaneous Localization and Mapping, which is a tool, a software package for a robot to navigate in an environment that it's never seen before. Now, if someone who's been writing Python for 2 months is able to do that, something that's typically done by graduate students, fueled only by Red Bull and ambition, and a little bit of balls, you can do it too. All you have to do is Google one of these things and start learning. In fact, when I started robotics, a guy named Mason Turner asked me if I wanted to join the team. He was my micro PTA. And he asked me if I knew how to do something involving computer vision. And I said, yes, of course I can do that for you. And then later that day I went home and I Googled computer vision for the first time. And I got it working. It worked. And now I have jobs doing computer vision, 2 jobs currently. And, anyone can do that. I'm not a special person. I don't think I'm particularly clever. I just know how to talk. I don't know. But if you start doing any of these things, and you start learning it, you'll be able to do it. All it takes is a willingness to keep working and not give up. All you have to do is not give up. Just don't give up. That's all it takes. There are Einsteins in this world, and there are Forrest Voigts in this world, and they're geniuses. Most people are not geniuses. How many of you know Forrest Voigt? So Forrest Voigt is a member of the Machine Intelligence Lab. So Forrest is one of the most incredible human beings I've ever met. On the drive to a competition we went to last year, we go into the truck, into this van we're driving in, and he, while driving to Kentucky, writes a full three-dimensional simulator, not using OpenGL. He wrote his own software renderer. His laptop was on battery when he did this. Just the whole drive he does this, and he's like, oh yeah, so I made the simulator, yeah. I don't know, Forrest is incredible, unbelievable guy. If you ever get the chance to meet him, worship at his feet. These are things you can learn about them. I don't know, take a picture if you're interested, or talk to me after. Most of these are very easy for beginners to learn, except the point cloud library, which is extraordinarily complicated, widely regarded as one of the most complicated pieces of software ever written. However, all the other things are pretty simple.
You said point cloud library?
Yes. Are you a point cloud person?
No.
Oh.
I'm just asking.
Yes, point cloud library. So I can show you some stuff with the point cloud library if you want to talk to me after. But so, for example, the Kinect publishes a point cloud. It's called an RGB point cloud. Each data point is a colored point in space, which I hope makes sense. It is determining depth of field, and it also has color. It composites those, creates a colored map. So a lot of robots navigate using point clouds. It's basically a way of interpreting three-dimensional data, segmenting objects in an environment, and so on. The other things I won't go into too much depth, but important things that are relevant to you guys, I think most of you are CS, is device drivers. So writing software that controls hardware, planning. So not actually, business major planning. Planning in the sense that the robot, given a bunch of information, needs to figure out what it needs to do in sequence, and that's a subset of AI. And Bernie, I'm looking at you. You need to come and work on that. Other stuff. So we do other stuff. Robot plays chess. Robot automated painting. Those two pictures are not of our robot, but it does this thing. Don't know why I have this slide. There's Dr. Schwartz. Look in the background, you can see right over there the rubble of last year's competition ground. I don't know. So this is our Oculus Rift. We have 3 of them. We are working on this project for Lockheed Martin. But somebody asked a question, what would happen if my eyes were placed like a hammerhead shark? So we forwarded the camera data into the Oculus Rift, and then put the Oculus Rift on our heads. And the answer is, you throw up. But not to be discouraged, we tried putting them in a few other configurations. For example, pointing out from the side of your head. Again, you throw up. Putting them behind yourself to give you third-person view. That actually works. It's really cool. And then another one is pointing it backwards, so you can, for example, look forward at an audience while reading the presentation by doing this. Turns out that also makes you throw up. But if you mount them on the front of your face, it works pretty well. This is our project for Lockheed Martin. They gave us $30,000 to plant cameras on the front of the Oculus Rift and then make it work. It turns out that's actually pretty complicated, but I think it's a hilarious project to give a bunch of undergrads. It works right now. In fact, I brought my Oculus Rift, but I was late, so I had to run, and I only brought the robot, not the Rift. Why IEEE? I'm recruiting you now. For experts in the uninitiated, at least 7 former and current team members have worked at SpaceX. As you can see, we're very enthusiastic about SpaceX in this neighborhood. We write code for the boat and the sub. We write code for the rocket team. So we're writing autonomy for the rocket team's rocket assembly robot. Code reviews, outlandish things. So one of the core things we do are outlandish things. 6 months ago, we said an arm was impossible. And that was the reason we did the arm. Now we have a working arm. Everything we do is somebody comes up, we're sitting in a room, and they say, what if we did X, Y, Z? And everyone says, that's stupid. And then we do it, and it works. That's the way I think most things are done. Except at different companies, it's phrased a little bit differently. But ultimately, when SpaceX was founded, Elon Musk looked at Tom Mueller and he said, what if we built a reusable rocket? And Tom Mueller said, that's stupid. And then they did it. And in fact, December 16th, SpaceX is landing a rocket on a barge. You should all pay attention to these. Did you have a question?
Yeah, does that robot play basketball?
Not yet. Why?
I think IEEE made one somewhere.
Oh, yes. Have you seen that video? So last year,
I did a while ago, yeah.
there was a robot that played something similar to basketball. I can show you a video of that. So I worked on that robot. I did the computer vision for that robot. That was last year's robot. Yeah, I'll show you a video of that. But there was a robot that played basketball. Go ahead.
You have it in mind.
Oh.
I'm curious.
Oh yeah, it's not on. Okay. Well, how do you get involved? You can email me, jpennicoolum@ufl.edu, and no experience required. If you're interested in robots, you've got, metaphorical balls. You don't have to have, you're not required to actually have physical balls, but, you have to be willing to put in hard work, care about what you're doing, be motivated, and you can succeed in this group, in this organization. You can ask Julio about that. Ask anyone involved in this team. Ask Madison. This is just get in, do shit, make it happen, go home. So other ways you can get involved, I don't know. Message me on Facebook, write me a letter, send me smoke signals, talk to an IEEE person after this. Oh, well, not class. Nobody look at that. That's all I have to say about that.